Good evening, my dear J27 and 26 aspirants. This is your Captain Shreyas, and welcome to the next class of work, power, and energy. We have already done what is work, how to calculate it, work done by variable forces, what is kinetic energy, and the most important work and kinetic energy theorem, right? That's what we have done till last lecture. Today, we're going to focus exclusively on potential energy and the topic of conservative forces, which is again related to potential energy, and then the potential energy graph part, which we are again going to discuss today, right? So all of this in today's lecture with your captain, with your captain Shreyas, who has been mentoring, guiding, teaching for a quite long time. And I did my BTech from NIT Nagpur, research from IIT Bombay, and I want all of you to be better than me. I want you guys to study hard. I want you to guys, build a great career, and it all begins at 11th and 12th standard or when you're taking a drop, because this is a game changing era. That particular time of age of 17 years to 19 years, that's a golden period where whatever you have done in school, beyond that you take a big leap ahead and change your entire career, just because of what you have done in the last couple of years, right? And after that, you can obviously scale it up depending on which college you go to. So let's go ahead and let's make sure that we become really, really great. And for that, one of the first few steps is smashing that like button down there and hitting the subscribe button too, right? Hi Suresh, hi Jeffin, hi Bala, hi S3 Harsha, welcome Netaji. Can I crack top 10 rank in J Advance if I start my preparation after means I complete 50 chapters in advance before mains? So yes, Netaji, what standard are you in? Mental Science, and welcome. Hi Suresh, hi Prerna, welcome everyone. Hi Adarsh, nice to see you all back over here. Yeah, I hope you guys have seen the lecture number 1, starting off with lecture number 2, and I hope you guys have also registered. Need to constantly remind you guys. I was saying yesterday, a couple of you registered. Very good, guys. Keep it up. Smash that like button and subscribe. The MV set also you need to register. Very, very important, because a lot of prizes to be won, and it's happening near your city. Even if you are not able to go into it offline, online will also happen, don't worry. And scholarships are also there, and prizes also, and you will know where you stand. Very easy to register by entering your mobile numbers, right? Okay, cool. So good evening, Harsha. Yes, welcome aboard. Already done. Very good, Nandan. Hi, Shriparth. Good evening, my dear. Good evening. And keep commenting, keep chatting, because then I'll get to know your names. It will become very familiar, so that when I see your name, no, after 2 years, it will be very interesting, because I'll remember, oh, this student, it's my student. Okay, great. So I'll feel very happy when I see your name on the rankers list. I know you are going to crack it. Don't think, sir, what you're joking, Chumma. Don't put me on the tree. I'm a normal student. No, I feel that you are going to crack it. After 2 years, I'm going to see your name, right? Or maybe after 1 year, right? So let's begin with the concept of conservative forces and then the concept of non-conservative forces. What the hell is this? Conservative versus non-conservative. I will give you an example. Let's say, you know, I have a glass or something. Okay, this is not exactly a glass, but a beautiful pen stand which I got it from Sikkim, one of the best places on earth, I would say. Beautiful, beautiful state, and the people there are also very disciplined, very clean. I love that state. All right, so Sikkim, guys. So it's a stand. Let's say I have a cup like this, and I filled some water in it, and I'm walking, I drink some water, then some water gets spilled, oops, and then, I add some water onto it, then I collect some water from somewhere, again I drink, again spill, I add, and when I come back to the same place, I see the level of the water before and after is the same. So in this entire process, I started from this point and I went here and there, drank some water, spilled some water, drank some water, spilled some water, drank some water, spilled some water, added some water, yeah, and poured some water. And then again, I'm back to the same place and I see the level of the water is same. So I have conserved my level of water. Okay, what happened in between, it's okay, but I maintained the level when I'm back to the same place. That's very important. That is like conservative. Second one, now the second example which I'm going to give you is of non-conservative, where let's say I drank, I spilled, I poured some water, I drank, I spilled, I poured some water again back into this, I collected some water, but when I'm back to the same place, I see the level of the water is not the same. Earlier it was more, now it is less, or earlier it was less, now it is more. So the level of the water has changed when I come back to the same place after a round trip. That is like non-conserved. That is like non-conserved. Obviously, you have to compare when you have come back to the same place, not at two different places. Now, in terms of work, power, energy, if you go around a trip like this, you start from here and you come back. This is nothing but a closed path, closed path, closed path. And there is some kind of a force over here. If the if the if the work done, the work done in a closed path, in a closed path is always zero, then it is said to be conservative force. Then that force which is doing the work, then that force doing the work, doing that particular work is conservative in nature, is conservative in nature. That is very, very important. How do I represent it mathematically? If I move small amount, there will be a small work, and the work done, I can represent it as, let's say, dW. What is dW? This is nothing but the small work in small displacement. If I move small amounts and I want to measure the total work, then I will add them. Add means integration. But I'm coming back to the same place, starting and initial position is the same, then the symbol used is this. This is called as a cyclic integration or closed surface integral or closed line integral, or basically, closed loop integral, whatever. Okay, so basically it is called as a closed integral. Closed integral means, what is the meaning of closed integral? It means my initial and final is the same. I have covered literally everything. I have gone and covered everything and I have come back to the same place. Initial and final is the same. This addition of the work dW, 0.1 joules, 0.5 joules, 0.3 joules, minus 0.2 joules, minus 0.6, minus 0.2, minus plus, like that. If you keep adding and you come back, it is adding up to be zero. It is adding up to be zero. That is how I represent it mathematically. Then the force is said to be conservative in nature. This is how I show it mathematically. Is this absolutely clear, my dear warriors? Everybody, hi Jeffin, good evening. Hi Pritija, good evening. Nice to see you on time today. Hi Jolly. Yes. All right. Sudarshan, why not, man? You can also get all India rank 10. Why not? Is that your question? I think something else was your question. All right, I'm so glad you are in the pro batch and now have got a class at 6:30. No issues, it's Ria. You can always watch the replay of the class. You are always welcome over here, okay? And I'm so glad you are in the pro batch. All the best. I'm pretty sure you are going to be a pro very soon. Now, imagine, now imagine, now imagine what kind of forces can be said to be conservative, what kind of forces are said to be then non-conservative. We'll give two examples also, but before that, one last thing. Let's say, for example, from here to here I go, okay, let's say the work done is plus W1. Example, if I come back via some random path, the work done will be minus W1. Just think about it. If I come back via some other random path, the work done will be exactly minus W1. Why? Because the force is conservative. So if I do 2 joules here, it will be minus 2 joules here, so that the total work done will be 0. So if while coming back, I'm doing minus 2 joules, while going from here to here via some path, it is plus W1 joules. Think about it now. If rather I went like this along that orange path in this particular direction, then how much work will be done? then how much work will be done? So if I go from here to here, it is minus W1. So if I go from here to here, it will be plus W1 work. And do remember, these paths were randomly chosen. And first of all, this was minus W1 only because it was conservative in nature. This brings me to a very interesting concept that now, if I end up choosing some another path, also the work done to go from here to here will also be minus W1. And it also means that if I go along the same path in the opposite direction, the work done will be again plus W1. It will be plus W1 along this particular path. So whether I go from here to here or like this, as long as my initial point and final point are the same, the part doesn't matter, the work done is the same. So essentially, basically I can say that the work done is independent is independent independent of the path taken, independent of the path which is taken, as long as the initial and the final locations are the same. This is a very interesting property of a conservative force. Are you agreeing with this? Hi, Nuruda. You're just little late. Hi, Hanok. Welcome aboard. Yeah. All right. I will come to it, Jeffin. Is a stone tied to a thread also zero work? So can I say that the force is conservative? The answer to that is no, because just because you find once that the work done is zero does not make it eligible for it to be conservative. It has to be always zero. It's like saying, you are considered a good student when you never steal. So one teacher is seeing one student for one day and that student does not steal. Does not mean he is not a thief. Maybe when the teacher was not seeing him, that time he was stealing. Then he's still a thief. Just because you didn't see it does not make you a good student. So same way, when the force always ends up doing zero work, not just in one scenario, only then it is qualified to be a conservative force. Only then it is said to be a conservative force. Got it? There is a slight difference. That's why I've used the word always. This word always is very, very important. Always zero, not in one situation, but every single time. Okay, very interesting concept it is. But now if you talk about non-conservative forces, then if you go from one point to some random path via some random path back to the same original location, then you will find that the total work done in a closed path will not be zero for for at least for at least one closed path, for at least one closed path. Even if once you steal, you are a thief. It's not like, ma'am, I was not stealing 30 days, only 31st of the month I will steal. That's it, bro. Once you steal, no, you are a thief. It does not matter what you did on the last other days. Okay, one closed path, then it is said to be non-conservative in nature, at least for one path, at least for one closed path. This also means that if by chance you happen to go from this particular point to this particular point along this path and some another path and some another path, this work and this work will be most likely be different. So the work done depends on the path. The work done depends on the path taken. Depends on the path which is taken. Okay, depends on the path which is definitely going to be taken. This is very, very important. Okay, there are many good government colleges which are good at everything. I'm not really sure. There is no IIT also which is good at everything. How can some college be good at literally everything? There will always be some flaw. So it's okay to accept the flaws, and whatever you want, that should be good in that college. That's more important. Okay, fine. So what are the examples of conservative forces and non-conservative forces? Let's talk about the examples now, right over here. Okay, so what are the examples? Examples wise, conservative forces, gravitational force is a conservative force. Then, just like gravity, when you are in a lift, the pseudo force which acts on you also acts like gravity for that moment in a non-inertial frame. If you remember Newton's law, pseudo forces. So you would have seen in a lift, the formulas get replaced as A plus G, A minus G. Do you remember that? How many of you remember it? In the lift, the formulas get replaced. Instead of A or G, you will get A plus G, A minus G, like that. So even that A which has come in that A plus G or A minus G is because of the pseudo force. That pseudo force also is conservative because gravity is also conservative. So you will see that as well. So even the pseudo force in a non-inertial frame of reference, like a lift, is also non-conservative, it's also conservative in nature. Then you will also see electrostatic force. Electrostatic force is also conservative in nature. Even spring force is also conservative in nature. And even your, what do you say, elastic forces are also conservative in nature. And there are many such forces which we'll talk about when time comes. But gravity, pseudo force inside a lift, electric force, spring force, elastic force, all these are conservative forces. And kind of makes sense also, like if I lift a box while going up, gravity does suck out the energy because force is down, displacement is on the top. So it is doing negative work. When I bring that block back to its original location, it will end up doing positive work because force and displacement are in the same direction. So same is true for even electric force or spring force. I'm pulling the spring is doing negative work on me, but when I release the spring back, the spring is doing positive work and restores back it into the original state. So wherever restoration is possible, wherever reversibility is there, you will notice that those forces are conservative in nature. Okay, so elastic force, I pull a rubber band, it gets deformed, I release it, it comes back to its original state. So wherever you can get back to its original state without any change in the universe kind of thing, then you can say it is like conservative force. But there is always a spoil sport. Whenever there is a hero, there is a villain. You have the non-conservative force as well. Now that is where you cannot really get it back into its original state. There will be some change which is happening somewhere. Like for example, I push something from one place to the other. Friction will do negative work. Now while going back, friction won't say, oh, while going, I sucked away the energy from you. Oh, while you are coming back, I will give it back to you. Friction will be like, oh, you went like this. Like, I will take energy. You come like this, I'll still take energy. It's like toll. It's like paying a toll. Have you gone on a highway and you pay toll? You're going from one city to the other city. You see a toll booth, you pay the toll. While coming back, you cannot say, hey, I'm undoing the operation. So while going like this, I paid the toll. While coming like this, you give me the money back. That person will slap you and he'll be like, hey, I'll complain to you. Da. Huh? So what they will do? They will again take the toll only. So it doesn't matter which way you are going, how you are going, just give me the money. That's all. So friction also acts like that. You're going like this, that's it. It is taking the energy. You're coming back, again it is taking the energy. You come back to the same place. You have done some amount of work. Some energy is lost. The universe has changed. Things have changed. You are given the energy into the surfaces heating by rubbing against each other. So it's no longer the same even if you come back. Pandu went on a vacation and came back and he saw all his friends have changed. It's not back to normal. It's things have changed. So that is non-conservative. So there are many examples of non-conservative forces we can see. All right. Example, friction. Friction. Now, friction usually is the word which is used between two solid surfaces rubbing against each other. But you can also have liquid flowing on a solid or gas flowing over a solid surface or liquid surfaces interacting with each other. Then that kind of force is basically, which is the resistance force between liquids, gases, etc. That is called as viscous force. Viscosity is a separate chapter, separate topic in physics, which we'll be learning later on. Air resistance, you can say, or fluid resistance, that is viscous force. Okay. Even the normal force, even the normal force, or even the tension force, all these are basically non-conservative in nature. These are evil villains. Remember the faces, most wanted people, right? Friction, viscous, normal, tension, all evil people. They are not conservative. They will not come back to the same state. They will not do zero work. They will suck away the energy or give something. But these are power people. Gravity, pseudo, electric, spring, elastic forces. You come back to the same place. They have not done any work. It is brought back to the same original state and condition. Is this now clear? Okay. Intermolecular forces, electromagnetic forces, at the base level, electric forces are conservative. But when you actually use the electromagnetic forces in or consider it as friction, then what happens is it becomes non-conservative, because these electromagnetic forces will end up pushing the molecule somewhere else. They might break off the bonds, and once the bonds are broken or it is deformed, it has been like a permanent damage. Okay, so then it becomes non-conservative. All right. So if you look at it as a bigger, larger perspective, friction at the end of the day, what it is? It's an electromagnetic force. But that electromagnetic forces are permanently changing the structure. They are deforming it, right? So that is the reason why it becomes non-conservative. Okay. There is one more lecture, Jeffin, on this, right? We'll do power and energy conservation in the last class. Okay, perfect. I hope this is very, very clear. Sir, for me that the college fees want to be less, sir, that good with something. Yeah, there are most of the government colleges are lesser fees only, and there are a lot of scholarship fees, scholarship programs which run. There are also loan facilities available in most of the colleges, right? So all these things are there. Don't worry, Pritija. And you can also earn money while you are working in a college. Like we have so many people in Vedantu who we only coached, and they were working for us only in Vedantu as internship. So, we do that. Like I remember there was one student of Vikas sir who was working for me, in the content side a long time back. And he was our student from Ekalavya batch, and his family condition was not that great. And we supported him. He was earning good enough money, okay, for him to pay the college fees. So it was almost like he uh, paid almost nothing for his college for the, I think, almost 2 years or something. So all those things are possible. Anyways, coming back, now that we have understood what is conservative, non-conservative forces, I'll give you an example on this. Okay. So imagine you go from this particular point A to this particular point B. Then from B you go to C. From C you go to D. And from D you go to A. And it is given that while you go from A to B, the work done is plus 30 joules. When you go from A to D, the work done is plus 50 joules. While you go from B to A, the work done is minus 70 joules. Oh, okay, something like that, or minus, let's say, 80 joules or something. Then when you go from B to C, how much work will be done? Assume conservative force. Assume conservative force. That force is conservative, which is doing the work. So based on that information, can you figure out how much is the work done from B to C? I'll mark all the points right over here. This is A, this is B, this is C, and this is D. Let's see how do we do it. First of all, because the force is conservative, if I start from a point and I come back to the same point, the total work done should be 0. So I know that the closed integral of dw should be 0. So the work done from A to B plus work done from B to C plus work done from C to D plus work done from D to A. So I'm coming back to the same place, A to B, B to C, C to D, D to A. A and A is the same. So I'm back. So the total work done should be 0. Okay. What is the work done from A to B? It is mentioned to be 30 joules. Okay. Then what is the work done from B to C? Oh, that is what we have to find out. All right. So I'll leave it as it is, untouched. What is the work done from C to D? What is the work done from? Oh, I think one more information needs to be given. AB is given, BA is also given, AD is given, CD was missing. I'm so sorry, guys. C to D also needs to be given. Let's say C to D is something like 20 joules. Chumma, I'm putting up. Okay, some random number. That one information was missing. So work done from C to D. Work done from C to D is given to be 20 joules. Okay. Oh, sorry, guys. Sorry. This was not needed. This was not needed. By mistake, I gave this extra information here. This was not needed. So sorry. My bad. B to C. All right. All right. B to C. This was needed from D to C. D to C was needed over here. Let's say it is minus 80 joules. So sorry. I made the question only wrong. So sorry. This was D to C. Yeah. Now it is perfect. Okay. Yeah. A to B is 30. A to D is plus 50. D to C is minus 80. B to C is how much? Okay. So now I think it makes sense. All right. So over here, the work done from C to D. Well, D to C is given to be negative 80. So C to D will be plus 80. So it will be basically negative of negative 80. So negative of negative 80 joules, which will be then plus 80. D to A, well, A to D is 50. D to A will be minus 50. A to D will be negative 50. That's it. So this will be 0. So now we can write it down as 30 plus WBC plus 80 minus 50 is 0. 80 minus 50 is 30. 30 plus 30 is 60. So 60 plus WBC will be 0. Therefore, WBC will be negative 60 joules. That is the answer. So wherever forces are conservative, the net work done will be 0. If you know along the remaining paths and you are asked what is the work done in a particular path, you can just add up simple algebra and you will get the answer just because it is conservative. Perfect. So answer can be positive or negative. Yes. Now, why were we talking about conservative forces and non-conservative forces? It was exactly for potential energy, and you will understand why soon. Now, whenever I use the word potential energy, then you think of stored form of energy. You think of a stretched bow and arrow, or like a spring which is elongated or whether it is compressed, right? You take a spring, you stretch it or press it, or a trampoline. When you jump on a trampoline and the trampoline is pressed, then there is energy stored in it. Or a mass which is taken up, it has gravitational potential energy. Or when you take charges or magnets and you bring them close to each other, they have potential, electromagnetic potential energy within them, and when you release them, you see that energy coming out. So exactly, if you felt this in your heart, in your mind, then you are right about potential energy, because it is a stored form of energy. It has the ability to perform some work because of whatever is stored inside of it. So I can say potential energy is a stored form of energy, stored form of energy, stored form of energy. And because it is stored, it also has ability to perform work. It also has ability to perform, ability to perform work, ability to perform work. And whenever it is stored, it can be also used and again be restored. So, this particular energy which is stored. So, let's say, for example, I show it like a tank or something full of some water. Okay. So, imagine this is some tank. Okay. This is your stored energy. So, this is basically your stored form of energy, this particular thing. So, I can take it out, I can use it, and I can also refill it. I can also refill that energy. And this is possible in a cyclic order. I can use it, again bring it back. Like I take the mass on the top, it stores energy. I release it, it is being used. I again take the mass on the top, gravitational energy gets stored. I release it, again it gets used. I elongate a spring, energy is stored. I release it, energy gets used. Elongate, stored. Again release, gets used. So I can continuously do that in many number of times. It's not like going to get tired or anything. Okay. It's a reusable unlimited number of times. Perfect. Okay. Yeah. So having said that, let's also understand what are the different kinds of potential energy that you see in your day-to-day life. Example, yes, you have gravitational gravitational potential energy. You would have also heard about elastic potential energy. Elastic potential energy in a rubber band or a bow and arrow and all of that. Even a spring is elastic in nature, so you will also hear the word spring potential energy. Spring potential energy. You will also hear the word electric potential energy. And if you are from 9th and 10th also, you would be learning that maybe in your electromagnetism chapter. Electric potential energy, magnetic potential energy, all of that. All these examples immediately should ring a bell from our current discussion of conservative and non-conservative forces. Look at the names: gravitational energy, electric potential energy, spring potential energy, electric potential energy. You are not seeing the word frictional potential energy, viscous potential energy, normal potential energy, tension potential energy. No, never. It does not make sense. Can friction store energy? Like you do work against friction, it stored it. And when you went back, friction gave it back? No, never. Viscous force, can it store and give back the energy? Never. Normal tension? Never. These forces are the villains. I just told you some time back that these forces are basically the villains. Maybe there is a reason why they got that name, non-conservative, because they are not maintaining that energy. They're not conserving it. It's like saying you had that tank which had some energy stored. If you use it, okay, you're getting something, but it is not refilling that much. Maybe it's filling, if I take out 20 liters, I'm able to refill 1 liter. Or maybe I'm using 1 liter while refilling, I'm filling more. So, that balance equilibrium is not maintained. So hence, those forces never have associated potential energy because they cannot store and restore and reuse and refill faithfully. Whereas forces like gravity, elastic, spring, electric forces, conservative in nature, they can store, restore, refill, reuse it faithfully. So that brings us to a very important point over here. Conservative forces are only going to give rise to potential energy, or in general, potential energy is associated with conservative forces only. With conservative forces only. This is very, very important. This is very, very important. Potential energy can't be associated with friction, normal tension like non-conservative forces. Is this absolutely clear? Put up a fire emoji or a thumbs up in the chat box and smash the like button if you have not done that yet. Okay. Fine. I will not mention your name. Okay. Great. Shreyas Srinivas, you can find my magnetism class. You can just search for it on YouTube or just go to last year's Roar series or Nurture Pathfinder series. Pathfinder, you will get it. Just search for Pathfinder Magnetism Shreyas. You'll get it. All right. Okay. So you'll get it right over here. Just go to the channel only and you will be able to search. Just search like this. Magnetic and Shreyas. Magnetic Shreyas. Wow. See, this is magnetic Shreyas. Magnetic sources. See, this is a big playlist, 7 videos, 8 videos. So many things are there. Okay. Cool. Okay. All right. Having said that, that potential energy is associated with conservative forces. It is the ability to perform work. It is a stored form of energy. How do we exactly calculate this potential energy? Okay. And how do I know whether it is more or less? That also I will tell you. First of all, understand this particular energy, potential energy, depends on the configuration configuration of the system, or basically in simple words, how it has been arranged, the arrangement. How you arranged it does not matter, and does not, and it does not, it doesn't depend on how it was configured. And it does not depend on how it was configured. What do I mean by that? Okay, I'll tell you. For example, out here, I have a scale which is elastic in nature. I pull it, I can see it is elastic, so it has energy stored. And how do I know it has ability to perform work? How? Release it. See, it did work. Tush, it moved. If there was a bullet over here or some ball, if I release it, tuck, that energy would have gone to that ball, the ball would have gone flying, isn't it? So definitely it has stored form of energy. Okay, so it is potential energy. Now, what does this mean? Depends on the configuration and does not depend on how it was configured. Meaning, right now it is configured like this. It has been bent into an arc. The molecules are strained, stretched, whatever. So right now, because the manner in which it has been placed or arranged, it has energy stored. It does not matter how I got to this. Maybe I did this like this I did and got it like that. Or simply it was flat and gently I did this. Or it was like this. I bent it like this, like this, like this, and then I got it like this. As long as I'm coming back to this state, situation, arrangement, it will have that potential energy. Simple. Okay, it does not matter how you reach it. Same way, I take something and I place it here, it has potential energy. Now, it doesn't matter whether I go like this or like this or like this or like this. Doesn't matter. The potential energy stored in it will be the same. And the hint comes from the fact that potential energy is associated with conservative forces. And just some time back, I told you that the work done by the conservative force is independent of the path taken. It is independent of the path which is taken, right? So it kind of makes sense now that energy is only dependent on the situation, not as a path function, not on how you arrange it. So if I'm given two arrangements, the scale is like this versus like this. Can you tell me which one has more energy, which one has less energy? There is some configuration like this, whatever. Can you figure out which configuration has more energy versus less energy? So there is one configuration like this versus some same particles in a different situation. Okay. How do you know that this has more energy or this has more energy? There is a very simple way. Check its mental state. Give some emotion to that object. You will understand whether it is feeling happy about it or unhappy about it. Tell me this same scale like this versus like this. Two configurations. This is configuration 1. This is representing a configuration. Configuration means arrangement of particles, molecules, whatever. Versus configuration 2, which is bent. Tell me, in which of the two states do you think the scale will be unhappy or feeling uncomfortable, feeling a little bit sad, feeling a little bit distressed? Like this, when the scale is flat versus the scale is bent. Come on, answer it in the chat box. Answer it in the chat box. Yep. Tell me. Obviously, yeah, the second one, it is feeling a little bit uncomfortable. It is like sad over here. So if I give some emotion to it, this configuration is little bit sad. This configuration comparatively is happy or maybe less sad. You just need to compare whether more sad, less sad, happy, more happy, less happy, like that. Always the configuration which is sad, unhappy, or uncomfortable, then that will have higher potential energy. Higher potential energy. And the configuration which is happy will have lower potential energy. They say, right? People who are very happy, they are not bothered only. Low potential energy. But people who are very sad, always worried. They are always thinking high potential energy, high IQ people, they say. Okay, so this is definitely more than this. Is this absolutely clear how to compare the two situations? Lot of people think, you know, height is more potential energy. Guys, don't get me wrong, height is only a very specific example of gravitational energy. I was talking in general, not just gravitation wise. Sir, if I take it up, more energy. That is gravity. What about spring? Height only matters? No, it can be like this also, spring. So that is why, in general, situations where uncomfortable is where you feel uncomfortable, that is higher energy. Where you feel comfortable, that is lower energy. Simple. Okay. Simple. All right, Jeff in second one. Okay, perfect. Hi Yogesh. Hi Okera. Yes, perfect. Awesome. You guys understood it, I guess. Now, let's calculate how much is this potential energy in general. Say for example, there is a system, it is configured like this, and you change the configuration to like this. And in this process of changing the configuration, you are basically changing the arrangement configuration. The energy will change, potential energy will change, and this can only happen maybe because some external force did some work or whatever. Okay, so let's say from this situation to this situation you have gone. Okay, from this situation to this particular situation you have gone, and let's say in this particular process, there was some external force, and there was also internal force. But while changing the configuration, please remember, kinetic energy was constant, because I am interested only looking at the potential energy. So I don't want other things to change. Chemical energy, biological energy, blah, blah, blah should not change. Every other energy is same. Only potential energy is changing because I want to make that calculation right now. Okay. So imagine this. If I ask you, I am doing some external work because of that external force. I am doing some work externally on something, meaning whatever that spring block arrangement was there, I am pulling this block. I am doing some external work on this system. Where will my work go? Answer it in the chat box. I am doing 5 joules of external work on this system, meaning maybe I'm pushing it or I'm pulling it. I'm doing some work. Where is it exactly going? Exactly, guys, the spring is getting stretched or compressed, meaning it is storing that energy. I am pushing this block up. So I am doing external work. My hand force is external force on this system. It is doing some external work. What is it doing? It is increasing the potential energy of the system. So can I then say that the work done by my external force, is nothing but changing the potential energy. The symbol for potential energy is U. Okay, in general, the symbol for potential energy is U. Don't use P.E. That might not look good every time. So U is the better symbol, like K is the symbol for kinetic energy. So external work done is the change in the potential energy. Now look at it otherwise. Because kinetic energy is constant, using work kinetic kinetic energy theorem, the change in kinetic energy is 0. Therefore, the total work done will be 0. Therefore, can I say the work done by external force plus the work done by internal force, both of them added will be a big fat 0. Therefore, can I also say the work done by external force will be exactly negative of the work done by the internal forces. Whatever work you do externally will be the negative work done by the internal forces. If that is the case, I can just say minus work done by my internal force. In this case, my internal force is over here will be equal to delta U. Can you guess what those internal forces are? Those are like spring forces, gravitational forces within that system. So that internal forces in this situation is our conservative force. So the work done by the conservative force, the negative of it will be the change of the potential energy. A very important statement. Negative work done by the conservative force is the change of the potential energy of that particular system, and you can also add to it that is also equal to the work done by external forces. That is also equal to the work done by external forces. A very, very important statement, guys. Okay, if you want, I can block this also. Usually you don't use this, but chumma, I'm just adding onto it. Is this derivation absolutely clear? Give me thumbs up. Hi, Kamash. Perfect. All right. Any tips to study consistently without deviation? Harsha, just watch my lectures every single day. Watch our classes every day. Check my old classes. Then also talk to your friends. Have a good group. Friend circle is very important. Don't get into social media too much. Instagram, right? Snapchat, blah, blah, blah. Don't get into that too much. It is very demotivating because it creates a lot of addiction. Okay. And do some positive hobby. It could be as simple as drawing, painting, removing stress. It should be positive in nature. Do that, you will feel good. Yeah. Okay, perfect. Now, having said this, let's understand what it means. Let's understand what it means. That is very, very important. Say, for example, there is this box over here, mass over here. I take it here at this particular location. Okay, or maybe I just take it up. I just take it up like this. Okay, I'm taking it upward. I'm taking it upward. In this process, my external force, that means my hand will be there. So this is my external force. Will it do positive work or negative work? Think force and displacement in the same direction. So example, the work done by my external force, if I tell you, is plus 70 joules. Chumma some example I have given. Okay. Then in this situation, if you consider the mass and the earth together, both of them form a system, right? The mass and that earth, this is your earth, this is your earth, they form a system, they store a potential energy between them. So the gravitational force is that internal force. Gravitational force is that internal force, which is also the conservative force for the earth mass system. So if you ask me what is the work done by the gravitational force, now this gravity is your conservative in nature, is your conservative force in nature. Believe me, that will be exactly equal to minus 70 joules. Reason, the gravitational force will be like this. This is how your gravitational force will be. So gravitational force will be exactly opposite to the displacement. Both of them will be equal and opposite. So if this does plus 70, this will do minus 70. If this does plus 6, this will do minus 6. If this does plus 100, this will do minus 100. So exactly opposite of it. And whatever work you did, where will it go? It will go in the change in the potential energy. So if you ask me how much did the gravitational potential energy change by, I will say it will be exactly 70 joules. Because if I did 70 joules of external work, it got stored. And this kind of makes sense also that my gravitational force did negative work, meaning it sucked away 70 joules of energy. It is taking that energy, but don't worry, it is not dropping it anywhere. It is storing it faithfully in the form of potential energy. That is how you interpret this numbers. Say, I'm not interested in doing very complex problems now because many kids don't even know what potential energy is truly. They don't understand why this equation is valid. What is the meaning behind this equation? Yeah, everyone? All right. Very good. Okay. YS, don't spam over here. You will be blocked by the admin. Okay. So make sure you are not spamming. Yes. Great. So as you can see over here, I pushed this, it went up. If I did some 100 joules of work, gravity is doing negative 100. And when it is doing that negative 100, we should not be worried. It's a faithful friend, conservative force. So it is storing that in the piggy bank. It is storing it in the tank, right? It is storing it in the potential energy form. So extra 100 joules will be there. So same thing, you can do it for any other force or any other potential energy. Cool. Did you get this concept? Okay. I can do the exact opposite also, maybe for a spring as well. Say there is a spring which has been stretched like this, and it is released slowly so that it comes back to its original state. So this is how it moves. This is how the displacement is. So in this process, okay, as it comes over here, because I don't want it to speed up, my external force will be like this. External force will be like this. Whereas the spring force will be in this direction. Make sense? I don't want it to accelerate. I want it to come slowly to this situation and stop over here. Okay, it has stopped. If it has to stop, I will do work against the spring force. Spring force is this way. I'll be like, hey, don't come and hit my face. Come slowly. So I'm acting opposite to the spring force so that it arrives and stops over here. So here in this situation, if you ask me external force, how much work it is doing, positive or negative, force is opposite to the displacement. So the work done by my external force will be definitely negative. Let's say minus 20 joules. Random value I have taken. If you ask me what is the work done by my spring force in this situation, exactly opposite to external, in the same direction as displacement. So it will do positive work and it will be exactly plus 20 joules. Okay, it will be exactly plus 20 joules. Lastly, if I ask you what is the change in the potential energy, what is the change in the spring potential energy, then the answer for that, well, whatever work is done externally will be this, or the negative of this will be this. That's the formula. Yes, it will be exactly minus 20 joules. And it makes sense. When the spring was stretched, it had more energy stored. When it is here, it is relaxed, it has less energy. So from more energy to less energy, there is a decline. So energy change will be negative because it has reduced. So I hope now you have understood and convinced of this particular equation. Minus work done by conservative force like gravity, spring, elastic is the change of potential energy is also work done by external force. Absolutely clear? I am a new student. Welcome everyone. Okay. All right. All right. Okay. So Harsha, maybe you can put it up as a comment. I will definitely respond to you because you have put so many chats, and like I said, we'll be having a conversational, session very soon. Okay. Great. So now can we calculate the value of the potential energy? Can we calculate now the value of potential energy? The answer is yes. I'll tell you very important thing that when you calculate potential energy, the value of it has no meaning, but it is always measured with respect to something which then has some meaning. What's some very hi-fi stuff you spoke? I'll repeat again. The real value of potential energy, I can take it anything. It has no meaning to it. Okay. Actually, meaning is there when you relate or measure it relative to something. Okay. Relative energy has meaning. Absolute value has no meaning. Let me give you an example. Say this particular box is there over here again, and it is taken over here. We all know this is going to have low potential gravitational potential energy. This is going to have higher gravitational potential energy. Now, there is a student who says, sir, when you place this box on the ground, the potential energy is 0 joules. When you take it here, sir, I saw that the potential energy is 30 joules. Okay, fair and fine. Another student says, sir, I felt this over here has 0 joules. But when I go down over here, the energy is minus 30 joules. Another person says, sir, I thought 0 joules was somewhere here, sir, and this is 10 joules, sir, and this is minus 20 joules. Another person says, sir, I thought 0 joules was here, sir, and this is 10 joules, sir, and this is 40 joules, sir. Everybody is measuring 0 joules to be at some weird location. But one thing everybody will agree on, the difference of the energy, 30 minus 0, 30. 0 minus minus 30, 30. 10 minus minus 20, 30. 40 minus 10, 30. The difference of the energy is the same. So what matters is the relative potential energy or the difference of the energies, and absolute values you can take it anything to be 0. Accordingly, other energies get adjusted. It's like you can slide that 0 anywhere you want. Accordingly, all the other values will get adjusted relative to that 0, but the differences will always be maintained. Very, very important. So I'll make that statement over here. The value of potential energy is not significant in itself, is not significant in itself, but the difference in potential energy is significant, is significant, is significant. So this is not significant, the value of the potential energy, but the difference of the potential energy is significant. So you can take any particular location to be 0. You can take this location to be 0, this location to be 0, this location to be 0, this location to be 0. This is called as zero reference. Zero reference. Zero reference means it's your choice basically. It's your choice. It's your choice where you want to take 0. Irrespective of what you take 0 as your reference, the difference will always be the same. That's what I have shown in this particular example. Is this understood in your head? Let me know quickly in the chat box. Battery also has potential energy. Yes, because it has ability to do work. Electrical energy, it is there. Hope you are doing great, great, great. Yes, going to crack WP2. I'm so glad. Thala 7, welcome aboard. And Thalapati fan out here. Okay. Hi, Naveen. Welcome. Sir, can I get the job when I'm studying college? Definitely. Why not? Why not? Just get in contact, but it depends. That time openings, everything. So definitely, if something is there, just message us and we will definitely take you. In fact, many of our students are now also working in tech as coders. Some students have joined, some business department or some admin department also. Yeah. And some students worked with us as interns, then went to other companies. So yeah, that's the bond which we share with our kids, right? Because you're not just our students, you are slowly going to become entrepreneurs and you're going to become industry leaders, and we would definitely love to help you all. Okay, great. Understood. So now that we understand that the difference of potential energy is important, let's calculate the difference of energy in gravity and then spring. We'll not do the calculations for electricity, magnetism, or other things, because for 11th grade only those two are important. When in 12th standard you see those derivations or whatever. Okay. So now let's talk about gravitational potential energy. Gravitational potential energy. So let's say you have a mass and you are moving it here by some height. Okay. Then the change in gravitational potential energy, which by definition is negative of the work done by the gravitational force, which is nothing but the gravitational force itself dot producted with the displacement. Dot producted with the displacement. Now, as you can see, the gravitational force acting on it will obviously be m into g. The displacement is upwards. Can you see that? I'm moving it like this in this scenario. So they are both opposite of each other. So it will be nothing but mg multiplied by displacement, which is itself h, multiplied by cos of 180, because they are opposite of each other. What is cos of 180? It is -1. Minus and minus will become plus. So minus and minus, right? This will become minus mgh. It will become plus. So therefore, my delta U gravity will be mgh. So mgh is not the gravitational potential energy formula. It is the difference of the gravitational potential energy formula. Got it? Many people remember it as just potential energy. No, it is the difference. So mgh is the difference, like 30, 30, 30, 30. The 30 is mgh. Okay, because 40 is not mgh, 10 is not mgh, 0 is not mgh, this 30 is also not mgh. 30 minus 0 is mgh, 0 minus this is mgh, this minus this is mgh. The difference of the energy is mgh. Got it? All right, perfecto. Similarly, we can also then talk about spring potential energy, but before that, just a quick recollection of spring force. Okay, quick theory of spring force. If you take an elastic body like a spring, okay, and you either extend it or let's say you compress it like this. So say for example, I pull it like this by x. So this x is then called as the extension, and originally the spring was said to be in its natural condition. It is unstretched. Now it has been stretched by some amount, let's say x. Then the spring will apply a force on you in the opposite direction. The force of the spring, the force of the spring will be in this direction on you, whereas you will be applying the force in this direction externally. You are pulling the spring, spring is pulling you in this direction. It is found that this particular magnitude of the spring force, which is also numerically equal to my external force, okay, numerically equal to my external force, is found out to be proportional, is found out to be proportional to the extension, is found out to be proportional to that extension or compression, which is basically your x, is proportional to the extension. So in general, I can say that that particular spring force, let's say for example here, the spring force, replace that proportionality with a constant, is equal to k multiplied by x. But notice, if x is this way, the spring force is the other way around. So if you write it in vector form, then you will notice there should be a negative sign over here. There should be a negative sign because the vector of spring and the vector of displacement or extension is in the opposite direction. So that's why this minus. But if you consider only the external force vectorially, then I will not need any minus. I can just put k multiplied by x. So it depends on which force exactly you are considering. The force which is applied by the spring or the force which is applied externally. Depending on that, minus will come or not come. But usually we consider spring force. That means how much force will the spring apply. So that's why usually you will see minus kx. Now what the hell is this k, sir? I'll come to it. But before that, let me block both of them so that you are absolutely clear. This k which is the constant of proportionality, is called as the spring constant. This is called as the spring constant. Also measures the stiffness. This measures the stiffness or softness of the spring. Stiff spring means it's very difficult to pull it or compress it. Soft spring means easily you can pull it apart or compress it. So stiff spring will have a very high value of K. A soft spring will have a very low value of K. Okay, that stiffness or softness depends on the material of the spring, depends on the diameter of the coil, spacing between the coil, the radius of that coil. All those things will define the stiffness. So all of this is determined by the material, all of this is defined by the material, shape and size of that particular spring. Okay, we don't have to worry about that. For us, spring constant will always be given. Lastly, what is the unit of K? The unit of K, as you can see, this is Newton, this is meter. So obviously it will be newtons per meter. 20 Newton per meter, 50 Newton per meter. If it is some 2000 Newton per meter, it is a stiff spring, a very low value. 2-3 Newton per meter will be a comparatively softer spring. Okay, so Newton per meter is the unit of the stiffness constant or the softness of that particular spring. Okay. Hi Jasveer, welcome aboard from 10th standard. Yes, minus 60 to minus 90 is still going to be 30. Exactly, Jeffin. So like I said before, where you choose the 0 really doesn't matter. The difference, as long as it is the same, that's it. That's what is important for us. So the 0 reference never ever matters to me. Now that we understand what is spring force, what is the work done by the spring force? So, sorry, the spring force's potential energy, my bad. The spring potential energy, my dear warriors, the spring potential energy. So again, what I will do, imagine I take a spring and let's say I stretch it by some amount, like so over here. This is how much I have stretched it. The spring force obviously will be here. Spring force will be here. So if I want to figure out how much energy is stored in the spring, it will be obviously negative of the work done by the spring force. Now, the work done by the spring force, there is a problem here. It is not a constant value. As you can see, it is variable. It depends on x. So it's a variable force. So I have to do integration. So it will be negative of integration will be there. Why integration? Because the force is not constant, of the spring force and small displacements from 0 to let's say x. Now, as you can see that the spring force itself is going to be minus kx, and this into dx from 0 to x, let's say, minus minus cancels. So I'm just left with k is also a constant, will come outside. Integral of x into dx from 0 to x. So what is the value then? It will be k x square by 2 minus 0 square by 2. Right, after substituting the limits. X's integration, x raised to 1's integration is x raised to 2 by 2. First put x, then put 0. So this is what you will get. So this is going to be just half k x square. That is nothing but your spring potential energy difference. But now, usually what we'll do, we will take this as our 0, the natural condition, as our 0 reference, when it is basically not stretched. It is not stretched at all at its natural situation. So the difference will be the final potential energy minus the 0 reference potential energy when it is not stretched at all, or when it is in its natural condition. Here it has been deformed. This is your spring which has been deformed. which has been deformed, this will be nothing but your half k x square. But since I defined that whenever it is not stretched, that value is going to be a big fat 0. It is going to be 0. So hence, in general, my spring which has been deformed has a potential energy of half k x square. That is the proper understanding and derivation of it. Okay, is this absolutely clear? This was the difference, but the difference I wrote it as final minus initial. This is final, this is initial. This initial energy is 0 because we say when it is not stretched, it has no energy. We define that 0. So as per that definition, it is half k x square. Is that absolutely clear? Okay. My God, Pritija, why do you want to not do a job which is not known to family? What are you saying? What is wrong? All right, so let's start with some questions now coming up on your screen. So all these are the important points. We have done potential energy in so much detail. Nobody will teach you like this. I'm guaranteeing you like that. And let alone any, you know, regional channel or even English channel which is there. Nobody can teach you like this. The way in depth which we have gone, guys. So yeah, we have done conservative, non-conservative, potential energy, what it is, what is the meaning, the formula, the reference, 0, spring potential, gravitational potential. Now let's start with some questions. Which of the following forces cannot be expressed in terms of potential energy? This was asked this year. Frictional force, Coulomb force, restoring force, gravitational force, which cannot be expressed as potential energy. Yeah. Let's see how many of you can do this. Welcome, Jasveer. Yes. All right, Jeffin, understood. Sahana, that will happen. I'll whatever it is, I'll tell you in the DNA batch. Okay, let's not go into DNA batch on a JEE channel. Okay, we'll come there. Anyways, I'll be meeting you on Saturday, right, in the DNA batch. Okay. So, my dear students, over here, you have to just check whether it is conservative or not. This is conservative, this is conservative, this is conservative. Restoring means elastic. This is not conservative. So I think it should be option A, perfect. Friction A, yes, it is non-conservative. So non-conservative forces cannot be associated with any kind of potential energy. That is something which I mentioned right over here. Potential energy is associated with conservative forces only. And friction, like we saw, is a non-conservative force. Only gravity, restoring, elastic forces, they are conservative in nature. Alrighty. Moving on to the next question on your screen. Assertion reasoning kind of question. In a central force field, the work done is independent of the path chosen. Again, a JEE PIQ. Every force encountered in a mechanics does not have an associated potential energy. In the light of the above statements, choose the most appropriate answer from the options given below. Wow, what a question, guys. In a central force field, the work done is independent of the path chosen. What is the meaning of a central force? Like, say for example, there is some object here. The force between these two objects, let's say this object gets pulled here. If you place it here, it is pulling it like this. This is here, it is pulling it like this. This is here, it is pulling it like this. This is here, it is pulling it like this. This is here, it is pulling it like this. As you can see, always the force is directed towards the other object. That's why it is called central force. If it is not central, that means this object is here, this is here. The force is in some weird direction. When it is here, then it is in some other direction. Then when it is here, it is maybe like this. Then when it is here, maybe it is like this. As you can see, the forces are going little bit skewed manner. This is not central. This is non-central kind of a force. This is non-central kind of a force. This is basically your central force. Now, which are the examples of central forces? Obviously, gravitational force, electric force, all these are central forces only. Two masses, gravitational force. Two charges, electric force. Two magnets, magnetic force. Gravitational force, electric force. They are always central forces and they are all conservative in nature only. They are all conservative in nature. So and whenever it is conservative, it is independent of the path chosen, the work 100% because it is conservative. So assertion is 100% correct. So assertion is definitely correct. This much part we understood. Every force encountered in mechanics does not have associated energy. In the Yes, every force which we encounter in mechanics, like it does not have potential energy. Why? Like example, friction. Friction. It is also a force, but it does not have potential energy. Why? Because it is non-conservative in nature. Because it is non-conservative in force. Yeah. So every force in mechanics does not have potential energy. Very true. Some forces have, some forces do not have. But is this the reason or explanation? I think there are two correct statements, but they are not explaining each other. Like, I mean, whatever I explained over here, where did that concept of every force having potential energy come into play? No way. So hence, both are true, but they are not the correct explanation. Okay, reason is not the correct explanation of the assertion. Is this absolutely clear? Everybody with me? Understood? Awesomeness, guys. Let's move to the next question on your screen. This is a PYQ. A body of certain mass is lifted to certain height from the ground in two different ways as shown. The ratio of the work done against the gravity in both the scenarios is case 1, you're just pulling it up. Case 2, you're taking that same mass, but you're going like this. Where will the work done be more or less? What is the ratio? As you can see, when I'm taking this from here to here, this was its initial level, this is its final level. Here, it was here, and then finally it is here. The height difference is the same, h is same, mass is same, g is same, so potential energy is also same, so work done externally should also be the same. So hence the ratio should be 1:1. Perfect. The answer is 1:1. Work done is also the same. So same work is done. Hence it will be 1:1. Height, same mass, same g. Now remember, gravitational energy only depends on the height. Does not matter where you are horizontally. So if you move horizontally, potential energy will not change gravity wise. But only when you go up or down, potential energy will change. No horizontal movement can cause changes. Yeah? Everyone with me? Yes, Sunita, whatever doubt you have, you can put it. If it is relevant to the topic, I will definitely answer it. Okay. Now, let me also show you one more example over here. Okay. Another example over here. A spring is stretched by X and energy stored is U. How much work is done to further extend by the same amount, to further extend it by the same amount? Very nice question. Let's see if you can figure it out. Earlier, the spring is stretched by X, energy stored is U. So energy stored and extension is related by half K X square. So we had our unstretched line, which is 0. You elongate it by X. The energy stored over here is U. Now you are further elongating it by X. So X and X together, that will make it total 2X extension. Here, how much will be the new energy stored? So if you calculate how much is the new energy stored, it will be half same K, but the total extension, don't put it as X, it is 2X now, right? So it will be nothing but 2 square, which is 4 times of half K X square, which is half Kx square is nothing but U. So it is 4 times of the old energy. Oh, interesting. So here the energy which it is stored is 4 times of original energy. Now the question is not how much energy is stored. The question is how much work is needed. If you change the energy from here to here, in this particular process, how much external work will be done? Logic says the work done by my external force is change in the potential energy, final, which is 4u, initial, which is u. So hence it will be 3u. So this is the external work done. 3u will be the answer. That extra work done will be 3. Is that clear? All right. Yep. Roar series, man, legacy. Instead of doing marathons, we are doing part-wise series. So this is not exactly roar, but this is, I would say, lecture by lecture series, because students also get tired, and colleges offline, everything is there. So that is the reason why we are keeping it lecture by lecture, so that we can go more in depth, detailed classes, topic by topic of all the important chapters out here. Okay. All right. Okay. Can we crack JEE in Jan? If you follow my plan, you can definitely crack it, Sunita. Just see the video which I put. I've given weekly plan. I've given the strategy for August to January. Everything is there on the channel. Please check it out. Okay. It's all there. Okay. Perfect. Now, let's see the relationship between force and potential energy. This is another important point. Just now, I showed you that my work done by conservative force is negative of the change of the potential energy. We just spoke about it. You can even put the minus sign even here, doesn't really matter. This is something which we just discussed right over here, isn't it? Over here. Minus work done by conservative forces, delta U. I explained it to you with examples and all of that. But let's say there is a small change. Now, this was for a big change. For a small change, I will say. So, this was for a big change. Now, for a small change. Now, for a small change, what can we tell, guys? For a small change, this will become small dW, small work done by that conservative force. That will be equal to, instead of delta U, now it will just become du. Okay. What is the work done formula? What is the work done formula? Work is force into displacement. So it will be minus that conservative force multiplied by that small displacement, let's say ds or dr, whatever you want to call. Okay, dr is that small displacement. This is nothing but small change in position. Small change in position. Interesting. Now, if I just calculate how much is that conservative force, that will be equal to, I will take the minus sign on the right hand side, du is there in the numerator, and denominator, that dr will go. Perfect. I think you have found out the exact relationship which we wanted. Relation between force and potential energy. But this is not any force, only conservative, like gravity, elastic, electromagnetic, only them. Friction, normal, you cannot use this formula because they don't even have any potential energy. So how do I read this equation? I'll come to it. U is the energy, du by dr is the rate of change of energy, but with respect to distance. Whenever there is change of something with respect to time, you just say rate of change of something. Like when hen is hen is there, and it is laying eggs. So how many eggs is the hen laying per second? So maybe it is laying 5 eggs per second. So that is the rate of laying eggs. But as the hen is laying eggs, it is also moving. It is doing cock, 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 and it is going somewhere. So how many eggs is it laying per meter? Rate of laying eggs as it walks per unit distance. That is then called gradient. So gradient of something means doing something per unit distance. So this is gradient of potential energy. This is negative. So I will say the conservative force, the final conclusion is the conservative force is the negative gradient negative gradient of its potential energy. This is the conclusion. The conservative force is the negative rate of change of its potential energy with respect to distance. As simple as that. Sunita, if you ask that question, you cannot crack. But if you follow the answer to your question, only then you can crack. So that's the reason why I said, please watch my video. I have already done it. Yeah. Even if you have board exams, I have given the plan. 99 percentile strategy from August to January, I have given the plan. Okay, sir, strategy also you gave, but I don't know what to do this week, next week, etc. No worries. I have given with the checklist, complete plan over here. Okay, you can check it out. All right. So all these videos are there only for you. Please do it. All right. Pritija, when you come to that situation, then contact me. Okay. Not now. When you go into the college. All right. Sir, can you give me some examples on this force and this one? Yeah. Why not? Imagine, I tell you, example that the potential energy of a body which moves in x is given by x-axis is given by x cube plus 4x minus 3. Okay. Question is, find the force as a function of x. Also find the work by conservative force from x equals to 0 to x equals to 1 meter. That is the question. Let's try to understand it, solve it step by step. Let's do first part, finding the force. Force and energy are related to each other by this equation, F is minus du by dr. So I can immediately say that my force is negative du by displacement. Displacement is only happening in x direction. So instead of dr, you will put dx. Okay. So where is my displacement happening? My displacement is only happening, small displacement is only happening along the x-axis. So that's why I am putting dx instead of dr. If it was happening in y direction, dy. If it was happening in z, it will be dz. So what if it is happening in x, y, z? Don't worry, we'll come to that later on. For now, just understand one dimension. Okay. Now, if you substitute the value, which will be minus d by dx of energy, which is nothing but x cube plus 4x minus 3. Okay, what is the derivative of this? X cube's derivative will be 3x square, 4x's derivative will be just 4, and minus 3 is a constant, so 0. So hence it will be minus 3x square minus 4 is that force. So we have got our answer. The force is minus 3x square minus 4 in newtons. Okay. Is this absolutely clear? Everybody with me? Everybody with me understood how to find out force from energy. Now the second part of that question, let's do that. Let's do the second part of that question, which says, find out the work done from this point to this point. Whenever you have to find the work, you need energy at both the locations. So first, let's do one thing. Find out the energy at x equals to 0. So u of 0. Substitute 0 instead of x. 0 cube plus 4 multiplied by 0 minus 3, which is just going to be minus 3 joules. Then find the energy at x equals to 1. Okay, put instead of x, put 1. So 1 cube plus 4 multiplied by 1 minus 3. So this will be nothing but 4 plus 1, which is 5. 5 minus 3, which is basically 2. So this will be 2 joules. Now let's go by our logic. The negative of the work done by conservative force is change in the energy. That means potential energy at 1 minus potential energy at 0. This is final minus initial. Final is 2, initial is minus 3, and this is minus of the work done. So this 2 minus minus 3 is 5. So work done by the conservative force will be negative of 5 joules. Will be negative of 5 joules. Understood? Is this absolutely clear? Everybody with me? Perfecto. Perfecto. Very nice. Amazing. Very good. So this is how you solve these kind of questions. Great. Now, sir, what if it is in 2 dimensions, sir, or 3 dimension? Don't worry. Even if it is in 2 dimension or 3 dimension, still you can use this concept. The only change which happens is, I'll tell you. See, this is all okay. Don't worry. This is a duplicate slide. Okay. So this is in general, whatever we have got. This is in general. Now, if it was a one-dimensional question in x direction, then I would just replace this with the conservative force in x direction will be minus. I will just take the rate of change of energy with respect to the x direction. Similarly, if it was in y direction, I will say Fy, and similarly in z direction, Fz will be negative of, this will be rate of change of energy in the y direction. This will be negative rate of change of energy in the z direction. So this is one dimensional in x, this is one dimensional in y direction, and this is one dimensional in z direction. So if it is all the 3 dimensions in combined, so for 3-dimensional question, what will you do? You are just going to say my net force vector is going to be, it will be fx vector plus fy vector, correct, plus fz vector. What will be my fx vector? Think about it. Fx vector will be exactly this. It will be nothing but minus du by dx. Fy vector will be minus du by dy. Fz vector will be minus du by dz. But this is the magnitude. I have to also put I cap, j cap, k cap. So I cap will be there. Here j cap will be there, and k cap, because this is vector form. These are the magnitudes of each one of them. So this is what it will be in 3-dimensional form. That's it. You differentiate it with x, with y, and z separately. Each components you will get it also separately. That's what you do in multi-dimensional questions. Don't worry, I'll give you an example of it so that it becomes less scary. Otherwise, it looks very big and scary, right? But actually, when you do it, it is very simple. So, say for example, my potential energy is given by x cube minus 2y or plus 2y square plus 5z. Okay, then I want to figure out how much is the force. This is what we are going to do. Essentially, what you need to do is find out each one separately. How much will be fx? It will be negative du by derivative with respect to x. When you differentiate this entire thing with x, that is x cube plus 2y square plus 5z, remember, I'm differentiating with x means x is changing, y and z are not changing. So this y and z are assumed to be constants, and derivative of a constant is 0. So this is just going to be derivative of x cube with respect to x, because other terms will be 0, and hence this particular part will be 3x square. Same way, if you try to figure out what is Fy, it will be minus du by dy. So when you do minus d by dy of this entire thing, x cube plus 2y square plus 5z, then in that situation, x is and z is constant, y is going to change because I'm changing y over here. So other things will be 0. So just differentiate this. So it will be just the derivative of y square, 2y square rather. So it will be nothing but 2 into 2, which is 4. So 4y. That's it. Oh, that minus sign also has to be there. I forgot that. So sorry, this minus sign. Same thing, when you find fz, it will be negative derivative with respect to z. So negative d by dz of x cube plus 2y square plus 5z. Rest other terms will be 0, only derivative of this. So 5 times d by dz of z raised to 1. So that is just going to be 5 only, but minus sign was remaining, so putting that. So if you ask me what is the total force vector will be minus 3x square I cap minus 4y j cap minus 5 k cap. This is the answer. X component, Y component, and Z component with IJK. This is the force vector. It's that simple. So whenever you are differentiating with a variable, the other variables are constant. This process is also called partial derivatives. Even if you don't remember the name, it doesn't really matter as long as you know the process. Anyways, you will learn partial derivatives in 12th maths a little bit. So partial derivative means when you are differentiating with a variable, the other variables are taken constant because you're only changing that particular variable. Nothing else has been changed. That is the answer. Perfect. Amazing. Understood. Let's do this particular question as homework then. We'll do this particular question as homework then. Will you be able to do this particular question as homework, everyone? Yeah, because this also has some x, some y and z. Easily you can do it now. The magnitude of the force in the at this particular point, how much is that force? Very simple question, you can do it. In fact, I'll give you a complex question now only. Imagine potential energy is x square z raised to 5 y, so go to y there, x square y raised to 5 z cube. Can you find out the force in general? Can you find out the force in general? Very nice question. Let's try to do this. First, let's find out Fx, which is minus d by dx of this energy, which is x square y raised to 5 z cube. Everything is constant except x. So y square will come outside, z cube will also come outside. X square's derivative will only remain inside. X square's derivative, how much is it? This is y square, this is z cube. X square's derivative is 2x. Same thing, do it for Fy, minus d by dz of x square y raised to 5 z cube. Okay, please remember this and this is constant here. Here y and z were constant. So what will happen? X square's, sorry, y raised to 5's derivative will be 5 into y raised to 4, and rest all terms will be x square into z cube. This has not changed. Remember, this has not changed. Here, y square and z cube did not changed. Yeah. Lastly, similarly do fz calculation. Oh, this minus was remaining. Just putting that minus. Always that minus we forget. Minus d by dz of x square y raised to 5 z cube. Okay. Here what and all is constant? Y and x is constant. So they will just come outside as it is. X square y raised to 5. Remember, they were just constants. And derivative of z cube. It will be 3z square. That's it. I found out my answer now. So my force vector will be, oh, by the way, I forgot the minus sign again. See this? Yeah. So the force vector will be minus 2x y square z cube I cap minus 5x square y raised to 4 y raised to 4 z cube j cap minus here 3 x square y raised to 5 z square k cap. That is the final answer. Is that absolutely clear? So whenever you are taking derivative, other things are constant. Just treat it like constants and do the standard operation of derivatives. And the end, add I cap, j cap, k cap separately and your job is done. Why 5, not 2? I think everything is fine over here. Just check this out. Yeah. In I cap. Oh, ho, ho, ho. Acha, I think while copying, we made a mistake. Yeah. So sorry. This was 5. I don't know why I made it square. So here also this will be 5. Thank you so much for pointing out that mistake. Silly mistakes happen like this. Yeah, thank you. Yeah, it was y raised to 5. Because so much x to y, it looks like some, some khichdi only is there. Yeah, it was like some noodles is happening over here, Maggi noodles. Yeah, x, y, z, squares, cubes, raised to 5. Yeah, yeah. Amazing. SMK question practice series is coming. A homework question, please do it. Okay, everybody, please do it. Right? Now, let's go to the last concept of equilibrium. Okay, let's go to the last concept of equilibrium, potential energy, and all of that. And then we will end the class. This you will need it more of 12th standard, but we'll just lay the foundation over here. Equilibrium. What do you mean by equilibrium? Equilibrium means the balancing of forces. So imagine there is a spring or multiple forces are there, conservative, and somehow all the forces are balanced. That means the net force is 0. So if my forces are conservative in nature and all the forces are balanced, then it is said to be in equilibrium. So equilibrium means that my net force is 0. But remember, we have just seen force is negative du by dr. So if force is 0, du by dr also has to be 0. So whenever there is equilibrium kind of condition, you will always see that du by dr will also be a big fat 0. Like for example, I'm balancing this pen somewhere. You will see the rate at which the potential energy will change in this situation will be 0. Or force is 0, net force is 0. Or spring is there, it is unstretched. Then force is 0, rate of change of energy with respect to distance at that point will be 0. So this is how it is. Now, I want to understand that when it is in equilibrium, sometimes the equilibrium can be stable, can be unstable also. It can be stable or it can be unstable. Let's understand what is the meaning of stable versus unstable. Say, I am holding this pen like this. It is now in equilibrium because it is not moving. I hold the pen in between. Now also it is in equilibrium because it is not moving. Net force is 0. I hold the pen carefully like this, balanced. I know if I do a little bit of or something, it is going to fall down. But right now, if I'm carefully balancing it, okay, then also it is in equilibrium. All the forces are just balanced. I feel that although this is also equilibrium, this is also equilibrium, and this is also equilibrium, the nature of the equilibrium is different. How? Let's understand. If I'm holding it on the top, it is balanced, but if I disturb it, tuck, tuck, what is happening? It's coming back. Oh, it's coming back. It's like teacher is teaching and some distracting element comes. Pandu is watching the teacher, somebody is walking, some bird is chirping, then you look at the bird, gone. But somebody is walking, some bird is there. You look over here, get disturbed, but no, I have to focus on the class and you come back. That is stable. So even when there is a disturbance, that disturbance, after it is removed, it comes back to its original situation. That is called stable equilibrium. Understood the meaning of it? Like this ball in this vessel. You move this ball here, it comes back. You move the ball here, it comes back. It is in equilibrium here, but that nature of the equilibrium is stable in nature. Okay, great. What if I hold it below? What if I hold it below? Now it is in equilibrium, all the things are balanced. You disturb it or you push it like this, it falls. You are in equilibrium, you push it this side, it will fall this side. This is unstable. You are watching, focusing on a class, somebody is walking by, oh, you got disturbed, tung, tung, tung. You went out of the class only. That is basically unstable equilibrium. Understood? So example is this. There is some kind of a mud or sand or pile. There is a sphere over here. It is balanced. You push it here, zoop, went off, got disturbed. You push it here, got disturbed. It's not like if you push it here, it will go here, stop and come back. No, right? It will stop and come back. No. Once disturbed, gone. This is unstable equilibrium. So this is All these are equilibriums only, but the nature of the equilibrium is different. So this is an unstable equilibrium. This is basically your stable equilibrium. This is basically your stable equilibrium. And the last one, you might be wondering, sir, what is it? Well, that is neutral equilibrium. What is the meaning of neutral? Say, when I hold it at the top, moving it here or here brings it back. When I hold it below, slightly moving it here or here takes it anywhere. That's it. It will just flow off. But when you hold it at the exact center, you move it like this, it stays there. You move it like this, it gets disturbed, but it stays there. You move it like this, it gets occupied over there only. That's it. That kind of equilibrium is neutral. Like for example, I push this ball here, it stays there, or it stays here if I push it this side. It's not like it's going to accelerate and go away, or it's going to get very happy. As happy as it is here also, here also. That is neutral equilibrium. So you can see that when you disturb them in any situation, say I move it here, this red lines are disturbances, disturbing here versus here. So right now, let's say these people in this kind of neutral equilibrium, it is somewhat like this. I'm attaching an emotion to it. They are neither happy nor they are sad. Flat poker face they have kept. Okay, they have kept poker faces, flat faces, nothing. In case of stable equilibrium, what happens is when you disturb it, this will become very, very unhappy because potential energy will increase. They will become unhappy. So that's why they come back, because becoming sad is worse than just remaining poker face. In neutral equilibrium, whether you move it here or whether you move it here, they will still have that poker face, stone face, no change, neutral. But in unstable equilibrium, what happens? When you move it here, they become extremely happy, low potential energy. Yeah, their potential energy decreases. So they become happy. That's why they never come back. Is this now absolutely clear? The difference between the three equilibriums and the condition, the state of potential energy, whether it increases or decreases upon disturbing them. And with the examples. Yeah, Harish, what is your doubt? Naku koncham Telugu telsu, Harsha. Yeah. So pendulum has stable equilibrium. Yes. This is a normal pendulum that has stable equilibrium, but this is inverted pendulum. This is unstable. Okay. I hope that is very clear, Harish. Sorry, not Harish, Harsha. Yeah. All right. Thermodynamics will take some time on how to make short notes. All right, Jeffin. But I'll tell you what, making short notes is a thing of a past. Nowadays, students are using flashcards. Number one, they are also using AI. So better to use these things, and I will make a separate video on that maybe. Potential energy curve. Now, imagine in these equations, whichever we did over here, the energy was changing with X or Y. Energy was changing with X, Y, or Z, whatever it is. So if you plot it on a graph, if you plot that on a graph, at this X, what is the energy? This X, what is the energy? At this X, what is the energy? That is called as a potential energy graph. What is this called? This is called as a potential energy graph or potential energy curve, because our energy will be some function of X or Y or Z. So you plot it with respect to X or Y or Z. That is your potential energy graph. Can you figure out whether it is stable, unstable, or neutral looking at the graph alone? The answer is yes. What is the essential condition for equilibrium? The essential condition is du by dr will be 0 or force is 0. What is the du by dr? What is du by dr? This du by dr, technically speaking, it is nothing but the slope of potential energy versus displacement. This should be 0. Wherever the slope is 0, that is exactly the place where there is equilibrium. Oh, can I find such places? 100%. I can see this is one such point. So if I draw a tangent, the slope should be 0. Yes, perfect. Here also if I draw a tangent, the slope is 0. And in this entire region only, the slope is 0. There is a big region where the slope is 0. I think I have got my answer. This point, and this location, all these places, these places are points or regions of equilibrium. Why? Because the slope is 0. du by dr is 0 in all these places. So quickly, I can just say that in all these places, I can say that over here, du by dr is 0. Here also du by dr is 0. And in this entire region, du by dr is 0. Okay. Can you tell me, although everywhere du by dr is 0, which of them is stable, unstable, and neutral? Notice carefully. Okay, one by one. Notice carefully, one by one. If you see, unstable means moving it left or right should make it happy, means lower energy. Oh, I think it is over here at this particular point. If you quickly think, okay, I'll show it here. If you see over here, sorry, if you see over here, it is making a poker face, but the moment you disturb it, either here or you disturb it here, you are disturbing it. It will become immediately happy. Immediately lower energy, low potential energy, it is becoming happy. So 100% this equilibrium over here is unstable equilibrium, because once disturbed, it just goes off. Now, if you see over here, in this situation, I feel it is like this situation, stable equilibrium. Let's say you consider poker face exactly over here at this particular point. Okay, now you end up disturbing it here or over here. You will see the potential energy increases. So potential energy increases, that means it will become unhappy. It will become unhappy. So it will want to come back over here. So this is stable equilibrium. But this scenario over here, again assume poker face, you move it, disturb it anywhere in this region, it will still maintain its expression, it will not change at all. So this entire region is of neutral equilibrium. So this entire region is of neutral region. This is neutral region of equilibrium, whereas this one is stable equilibrium. Here it is stable equilibrium. So looking at potential energy graphs alone, you can figure out whether it is stable or whether it is unstable or whether it is neutral. Is that clear? Now, if that is the scenario, what is the manner in which you can figure out whether it is stable, unstable mathematically? If you notice, wherever it is unstable, wherever it is unstable, it is also mathematically the maxima of the graph. And whenever you have a maxima of the graph, mathematically, it means the second derivative, d square u by dx square, should be a negative number. Whenever it is stable, it is the minima part of a graph. This is a valley point, which is a minima. That's where the second derivative will be a positive value. And wherever it is neutral region, then it is just a horizontal line, so which has zero slope. So d square u by dx square, the second derivative will be 0. It will neither be positive nor be negative. That is the validation, that is a check to see whether it is stable or unstable or neutral. That is how you do it. Okay? Everybody with me on this? So I will give you an example. Don't worry, I have put up the notes. So let me just give an example of this. Say for example, my potential energy is given by x cube minus 2x, or let's say x cube minus 24x is the function, plus let's say 5. Can you find equilibrium points? Can you figure out what are those equilibrium points, if at all any? I think we can do that. It's not a big task. Whenever there are equilibrium points, the first essential condition, what is it? The first essential condition, wherever there is equilibrium, the slope, the du by dr is 0. Wherever you go, the du by dr will be 0. Okay. So this is the most important criteria. So I will start off with that. So du by dr is 0. This is necessary condition. This is a must. This should happen. So here it will be du by dx, not r. Here u is x cube minus 24x plus 5. Basically, this should be 0. Okay. What is the derivative of x cube? It will be 3x square. It will be basically 3x square minus, this will be 24x, and let's say this is basically 5. So 24x's derivative will be 24. 5 is a constant, so derivative will be 0 only. Okay. Is this clear? So x cube's derivative is 3x square, minus 24x's derivative is minus 24. 5 is a constant, so derivative is 0. Okay, perfect. So just bring the 24 on the other side. So it will become 3x square is going to be 24. So therefore, x square will be 8. 24 by 3 is 8. So x will be plus or minus both 2 root 2. Both options are there. Plus or minus 2 root 2. Oh my God. Now you got two values of x. What do I do now? Okay. Let's take this on the top. After doing this, we have got two values of x. One place we have got x is equal to 2 root 2. Other value of x which we have got is minus 2 root 2. That means at both the places, at both these places, at both x's, there is an equilibrium. There is an equilibrium. There is an equilibrium. But the problem is I do not know which kind of equilibrium. Oh, I do not know which kind of equilibrium. How do I do that? Whether it is stable or unstable. That is the reason why I gave you the condition over here. Check the second derivative. Second derivative, whether it is positive, negative, or 0. Accordingly, you can figure out whether it is stable or unstable. Oh, is it? So let me find out what is the second derivative. So let's do that, guys. What is the second derivative of u? It is nothing but the derivative of the derivative. Already we figured out what is the derivative over here only, but still, if you want, it is right over here. Oops, what am I doing? Where is it going? Huh. So we know that du by dx was 3x square minus 24, just taking the first derivative. So the second derivative, d square u by dx square, will be 3 multiplied by 2x minus 0. 24 is a constant, so derivative will be 0. So this is basically going to be 6x. This is my second derivative. Here we will substitute the value of x and see what do we get. Okay, here we are going to substitute the value of x and then we will see what do we get. Let's start with this first. So d square u by dx square will be 6 multiplied by x. X is 2 root 2. Forget the value, but I know for sure this is a positive value. Here, if you notice, okay, in this particular scenario, second derivative d square u by dx square will be minus sorry, not minus, 6 times minus 2 root 2. Instead of x, I'm putting these numbers. 100% this is negative value. What happens when second derivative is negative? When second derivative is negative, it is a maxima and it is unstable. So, my dear students, this is 100% a maxima and this is going to be unstable. So, it is unstable at x equals to minus 2 root 2, and this is positive. That means it is a minima. Okay, it is positive. That means it is a minima. So definitely it is going to be stable. It is going to be stable at x equals to 2 root 2. As simple as that. Is that clear, everybody? No, this is the second last session. One more session will be there. All right. I'm so glad, Harsha. The concepts are clear. So this is what it means. And if you actually end up drawing a graph also, right? This is how the graph will probably look like. This will be the energy versus x. It is having minima at 2 root 2 and maxima at minus 2 root 2. So if you even draw the graph of it, I don't know, I'm just randomly drawing it. At minus 2 root 2, there is a maxima. So most likely it will look like this. At 0, it will be at 5, right? So it will most likely be like this. So this is your minus 2 root 2. This is where it is unstable. And this is 2 root 2 positive. This is where it is stable. So this is how that graph will look like. I hope it is now absolutely clear, my dear students, how to solve these kind of questions of stable and unstable. All right. So that's it for today, my dear warriors. And we are done. And I hope you enjoyed the lecture. Please solve the homework, like the video, share the video, talk about the channel, tell about Captain Shreyas sir and the Vedantu JEE English channel, which is for all the kids out there who want to learn in English medium with quality content. Even if you are Hindi medium, English medium student, doesn't matter. Still, this channel is just for you. But we are making sure that we give you the best content from the basics theory with examples and PYQs. Stay subscribed, like the video and share and comment below whatever answer you got for the homework question. Thank you. Captain Shreyas signing off.